Okay, we left off last time. We just started covering Heisenberg's uncertainty principle, and we talked about the fact that position and velocity are complementary properties, meaning that the more we know about one, the less we know about the other. Another set of complementary properties are electron energy and electron position. Okay, so the more we know about electron energy, the less we know about where it's located. These things are all important because information about electrons tells us the bulk of the information that we know about the chemical behavior of an atom, right? The chemical properties of an atom, the bonding of an atom, all of that's determined by the electrons and the electron behavior. So the fact that we can only know certain pieces of information about the electron at any given moment is pretty important when we're looking at chemical properties. So this monster right here is called Schrodinger's equation. Okay, and this is one relationship that's supposed to tell us some more information about the location of an electron than we would normally have access to. Okay, Schrodinger's equation is all about probability and the probability of finding an electron somewhere. And it looks like a big kind of like scary mess over here, but we're not so concerned about the math part of this. What we are more concerned with is what this thing means. All right, so if we break down the parts of this equation, we have this value here, which is called the Hamiltonian operator. Okay, that's going to be the total energy of the electron within the atom, all of the energy, the kinetic energy plus the potential energy. E will be the actual energy of the electron. And then this little trident guy, that represents the wave function, right? So that's the representation of the wave-like nature of the electron. So when we take Schrodinger's equation and we use it to make a plot of distance versus our little trident guy squared, this right here is going to be our probability density. That plot represents an orbital. An electron orbital is where our electrons are located around our atom. Okay, so this, for example, is what a 1s orbital would look like. All right, now you'll notice that it's a lot bluer in this region. Okay, so the denser the cluster of dots is, the more likely it is that an electron will be present there. The more sparsely located the dots are, the less likely you'll have an electron there. Okay, so that's what this sentence is saying here. The density of the dots is proportional to the probability density. You can also look at this in terms of an actual curve, okay, where you see that the distance over here, like when you are, trying to think of how to explain this in words where I don't have like, I guess you can, like, this is your R value, this is your R value. Your probability density is going to be higher the closer you are. All right, and you see how it falls off sharply once you get like that outer edge over here. That's represented by this part, the distance, you know, the distance has increased at this point. So this level of the graph is equivalent to this outer ring of the actual sketch. So that's where you're less likely to find an electron. We can represent the location of an electron in an atom using what are called quantum numbers. All right, the quantum numbers of an electron pinpoint its location and its properties as much as we can. All right, because like I said, it's you can't know everything about an electron, but we can sort of gather up as much information as possible in order to describe it. And there are 4 quantum numbers that we have to look at, and we have to know how to find them. We have to know how to use them, right? And we're going to go through them one at a time. The first is the principal quantum number, which is represented by the letter N. This is going to represent the energy level that the electron's located in. Okay, so if you remember that diagram of Bohr's atom from earlier in the previous lecture, the ring that was closest to the nucleus, that would be energy level 1. The following ring was energy level 2, energy level 3, etc. Now, N values kind of correspond to the periodic table. Okay, they correspond to the rows on the periodic table. So your first row of the periodic table is 1. Your last row of the periodic table is 7. So an electron can have an N value from 1 to 7. Okay, and the larger the value of N, the more energy that particular orbital is going to have. You can find the energy of an orbital using one version of Rydberg's equation. Okay, this, if you notice over here, that's 1 over n squared. There's only one orbital present in this equation, so you're only looking at the energy value for one particular orbital. Okay, so you could take this constant, this is your Rydberg constant, write that down, and know that constant. And now you could take 1 divided by the n value of your orbital, and that will give you the energy of that specific orbital. And this is what some energy values look like. You're going to notice that n equals 1 has the value over here, negative 2.18 times 10 to the negative 18. Look at this difference between n1 and n2. That is a huge jump. There is a significant energy difference between n equals 1 and n equals 2. And you're going to notice, and I think that there is another diagram of this somewhere in here, that as you move further away from the nucleus, the space between your energy levels gets smaller and smaller. So the difference between 2 and 3 is smaller than 1 and 2. The difference between 3 and 4 is smaller than the difference between 2 and 3. The difference between 4 and 5 would be smaller than the difference between 3 and 4. And that trend would continue. The second quantum number is the angular momentum quantum number. Okay, this is also going to designate the sublevel or the subshell of your orbital, and it determines the shape that your orbital takes. Okay, L is responsible for the shape that the orbital takes. Your L value can be any integer from 0 to n minus 1. Okay, so your L value should never be equal to your n value, and it should never be higher than your n value. It can go from 0 to n minus 1. And what's listed in this table below are the 4 most common L values: 0, 1, 2, and 3. These L values correspond to letters, right? Now we've heard about s orbitals and p orbitals. So these L values correspond to a particular letter, which represents a sublevel. So if you have an L value of 0, you have an S sublevel. If you have a L value of 1, you have a P sublevel. An L value of 2, you have a D sublevel, etc. Okay? And you guys should be familiar with S, P, Z, and F, right? You don't have to memorize the letter designations of anything else. And this is kind of what the orbitals look like. So your S orbitals are these spheres. They're very simple. Your P orbitals look like little balloons that are attached. This point right here, that would be like where the knot was, and that is like They call it a node. So it's a place where you would not have an electron, but your electrons could exist in either of these lobes. A d orbital looks like 4 balloons that are tied together. All right. And then your f orbital looks very complicated. There's actually one more d orbital as well, but I think we'll get a picture of that later on. Your third quantum number is the magnetic quantum number, which is m sub L. And your m sub L value can range from negative L to positive L. So, for example, here we have a 3d orbital. So I'm going to we're going to switch off real quick. I'm trying to do these fancy things with you guys to try to make things more clear. So if I have a 3d orbital, okay, that means that my n value is going to be 3. It means that my L value, if it's a d orbital, right, we just went over, 0 is S, 1 is P, 2 is D. So my L value has to be 2. That means that my M sub L value can be -2, -1, 0, 1, or 2. Those are the possibilities. All right. The final quantum number is a spin quantum number. That's m sub s, and that's going to describe how the electron is spinning within an orbital. So when 2 electrons are in an orbital together, they have to spin in opposite directions. So we designate one of them as an upspin and one of them as a downspin, but it's not really like one is spinning up and one is spinning down. They're just spinning opposite each other. So to differentiate the two of them, we call one electron plus 1/2 and one electron minus 1/2. All right, and that means that they're going to be spinning in opposite directions from one another. But those are the 4 quantum numbers. All right, so now we're going to just look at some examples of how we're going to use quantum numbers, just to make sure that we really understand the process here. So what are the possible values of L for n equals 3? Okay, so pause and think about this a minute. But if I have an n equals 3 value, that means that my L value can range from 0 to n minus 1, or from 0 to 2. So I can have a 0, 1, or 2. And that is equivalent to S, P, and D. What values of m sub L are possible for L equals 2? Well, we just did that one, right? If L equals 2, my m sub L values can be -2 to +2. All right, the first 3 quantum numbers, the n value, the L value, and the m sub L value, that describes one orbital, okay? Literally like you're trying to use a GPS to locate your electron. So here's a good example. We want to know what electron would have the following 4 quantum numbers, okay? And we're going to actually draw this out. Okay. So this is an electron diagram, okay? And we are going to use this diagram, and we're going to use our 4 quantum numbers that are up here, right? And we're going to figure out exactly where the electron that's being described here by these 4 quantum numbers would be located. When you're given a set of 4 quantum numbers, they're given in the following order. So the first number would be your n value. Your second would be your L value. I'll move that around in a second. Your third would be your M sub L value, and your fourth would be your M sub S value. Okay, let me just make it so you can see that real quick. Okay. So we're going to use each one of those numbers, and we're going to find the spot that it's talking about in this electron diagram. So first of all, if n equals 3, that means that my electron has to reside in one of these 3 areas, because the n value is 3 for all 3 of those sublevels. Okay, so I'm going to check that off because I used that one. Now, over here it's telling me that L equals 2. Well, which letter corresponds with an L value of 2? That would be my D sublevel. So my electron must be somewhere up here. Okay, let's check that off. Now my M sub L value is -1. Well, if my L equals 2 in my D sublevel, that means my M sub L can be from -2 to +2. All right, so let's look at what that breaks down to in reality. That means that each one of these orbitals has its own designation. Okay, my electron is in -1, so it must be in here. And my final quantum number is +1/2. Okay, that means that the electron that I'm looking at is going to have an upspin to it. So I just used my 4 quantum numbers to GPS locate my electron in a electron diagram. All right. Okay, now here are some interesting ways to do some counting with your orbitals and your sublevels and things like that. You might have to figure out how many sublevels are in a particular energy level. The number of sublevels are always going to be equal to your n value. Okay, so for example, if n equals 1, that means you're only going to have 1 sublevel available. That's the S sublevel. If n equals 2, then you're only going to have 2 sublevels available. That will be your S sublevel and your P sublevel. If n equals 3, you'll have 3 sublevels available, S, P, and D, and it'll keep going on like that. All right? You could figure out the number of orbitals that are in a sublevel by using the 2L plus 1 calculation. So if you want to know how many orbitals are in the S sublevel, well, that L value is 0. 2 times 0 is 0 plus 1. So an S sublevel must have 1 orbital in it. For your P sublevel, L equals 1. 2 times 1 is 2, plus 1 is 3. So a P sublevel rather, will have 3 orbitals in it. For L equals 2, which is your D sublevel, 2 times 2 is 4. 4 plus 1 is 5. A D sublevel will have 5 orbitals in it. All right, and so you could see that trend also. It goes from 1 to 3 to 5 to 7. And then the number of orbitals in any particular level of n. So like if I wanted to know how many orbitals are there in n equals 2, all right, I can break it down and I can actually look at every orbital in that level. Or I can use the n value and square it, and that will also give me the same value. But I think that we should probably look at it both ways here. So we have n equals 3. We have n equals 3 up here as an example. All right, so if we have n equals 3, that means our possible L values are 0, 1, and 2. Those are all valid L values for an n equals 3. If L equals 0, your M sub L value is 0. So there's only one orbital present there. If L equals 1, then your M sub L values are -1, 0, and +1. You have 3 orbitals there. If you have L equals 2, your M sub L values are -2, -1, 0, +1, and +2. You have 5 orbitals present there. So your total amount of orbitals in an n equals 3 level are 5 orbitals plus 3 orbitals plus 1 orbital, or 9 orbitals. Okay, what's 3 squared? That's 9. All right, so those are 2 equivalent ways to figure out the number of orbitals in any particular level. This is just a breakdown that you can, I mean, if you look at it and really study it, it might help you see the correlation between the n values and the corresponding orbitals. But back to the probability density and distribution, that all an orbital is, or all this diagram is like a description of the orbital. So it's a description of where we think the electrons are residing. Okay. If we look at the actual wave nature of this, these points here on the wave, these are called the nodes. Okay. And at the nodes, that is where the probability of finding an electron drops to 0. So you can have an electron anywhere in this space, but you cannot have an electron at a node. All right. And you'll notice in these diagrams that when you're going from, it's like, so you have a density right here, right? And you have this white ring over here. Then you have a density again. Well, that white ring here, that's equivalent to a node. That's a place where you will not have any electrons present. In a 3s, where you're going 1, 2, 3, you'll notice that you have nodes separating the different levels. Okay, and every time you hit a node, that's a place on your graph where the probability drops down to 0 that you're going to find an electron there. Okay. Do you remember that in terms of the shapes of these orbitals, that your angular momentum quantum number L is what will determine the shape? Okay, so your s orbitals are your L equals 0 orbitals. And they are going to have no nodes in them. You can always tell how many nodes a particular orbital is going to have with this relationship here, n-1. Okay, so your 1s orbital, no nodes, because 1 minus 1 is 0. Your 2s orbital, there will be a node, excuse me, there'd be a node between them, like we saw here, right? This is your 2s, there's your node. Okay, your p orbitals are lobed, like we talked about. They look like those balloons that are tied together. And the node is at the nucleus here. Now there are 3 p orbitals, we saw that. Each orbital looks like a pair of these tied balloons. And if you want to think about how they would be oriented, you would imagine one being in the x-axis, one being in the y-axis, and one being in the z-axis. All right, so you see this like 3-dimensional shape emerge of these different balloons that are tied together at the center. There is one node at the center for your p orbitals, okay? And the amount of nodes will correspond to the n level that you're at. So if you're at 2p, then it's 2. Your d orbitals, they mostly look like doubled up p orbitals, because they're these 4 lobed balloons. 4 of them are like that. Okay, so you have 1, 2, 3, 4, and then you have this one random shaped orbital where it looks like a balloon with a donut kind of around it. Okay. Don't go too crazy with like the names of these orbitals and stuff. Understand that there are 5 different d orbitals. Each one has a different name. And the name that it's being given is trying to describe the axis that it's existing on. All right. So like YZ, that's, you know, that's the axes that these lobes are existing on. So these little letters here are just descriptions of the location of the 4 lobes. That's all that means. Sometimes it's more helpful when you're starting to learn about this, where you would just call this D1, D2, D3, D4, and D5, just so you could start understanding the difference between them. And then later on, you can move into like understanding that your DZ squared is your weird donut shape, and the rest of them all are going to look like the 4 balloons together. And then your F orbitals just look like a hot mess. Okay. I'm not even going to try to describe the different shapes to you here. Just look at them. Okay. You don't have to be able to draw these or anything like that. We're just trying to understand how these shapes and relationships get more complex the further we are from the nucleus. All right. What is interesting though is that if you put all of these shapes together, they all fit together in a spherical way. All right. And this is actually why atoms are always depicted as a sphere. It's not like 100% perfect, but you could take all of these different shapes, including those crazy F orbitals, and when you put them all together and you try to like match them up like a puzzle, the shape that they form is a spherical one. So it all kind of works out. But that's a summary of the shapes of the orbitals. So here are some questions for you. What are the quantum numbers and the names of all of the orbitals in the n equals 4 principal level? How many n equals 4 orbitals exist? So hit the pause button here and try this out. Okay, there's all the information. These sets of quantum numbers are each supposed to specify an orbital. One set, however, is erroneous. Which one and why? So this is you having to go through each of the rules and figure out, you know, which one's breaking the rule here. So can n equal 3? That's fine. If n is 3, can L equal 0? Sure, it can be 0, 1, or 2. If L is 0, can M sub L equal 0? Sure can. M sub S is 1/2, that's fine. So A is fine. For B, can n equal 2? Yep. Can L equal 1 if n is 2? It sure can. M sub L is fine, -1. N equals 1, that's fine. L has to be 0 if n is 1. M sub L has to be 0 if L is 0. Over here, n equals 4, that's fine. L equals 1 if n is 4, that's a valid possibility. If L is 1, can M sub L be -2? It cannot be -2. It would have to be -1, 0, or +1. All right. Try it again on your own. I should probably tell you the right answer. Okay, so in this case, for each set of quantum numbers, there's something that's wrong there. Okay, so for choice A, if n equals 3, L can be 0, 1, or 2. But if M sub L is +2, L would have to be 2, right? So our new quantum number for that would be, let me get my little drawy thing. So we'll cross that out, and that should be 2. All right. If n equals 2, L can be 1, but M sub L could not be -2. So we'll cross that out. It could be -1, can be 0, or it can be +1. A little terrible commas in there. If n equals 1, L cannot be 0, or it cannot be 1 rather, it has to be 0. All right. Does that make sense? I feel like it should make sense. Oops. We're going to finish up by talking about energy, about electron excitation and relaxation. Okay, so that involves your electrons absorbing energy or releasing energy, depending on what they're doing. All right, because your electrons are going to be moving up and down from the different energy levels that they reside in. All right, so we call an electron an excited electron if it is transitioning from a low energy level to a high energy level. Okay, and the opposite of that is relaxation. An electron relaxes if it goes from a higher level to a lower level. All right, this totally makes sense. I mean, again, it acts like the electrons, they act like people. When we're excitable, we're going from a low energy level to a high energy level. When we're relaxing, we're going from a high energy level to a low energy level. So it's electrons being just like us, per usual. The difference here is what's happening, well, not the difference, but what we're going to look at here is what happens with the energy. So when an electron is relaxing, when it's going from n equals 3 to n equals 2, it is going to a lower energy level. That energy gets released in the form of a photon. Okay, so it gets released as light. When an electron goes from n equals 1 up to n equals 3, it can't just do that on its own. It needs to absorb the energy from something else. It absorbs energy, and then it's able to be excited up to that higher energy level. All right, so a lot of this is what I just said. Here's an interesting fact though. Each line in that emission spectrum that we were looking at earlier corresponds to a difference in energy levels between the two states. We kind of looked at that in the picture of the different wavelengths that were being emitted as the electrons transitioned down energy levels. So this mess right here is how we track energy transitions in this case in hydrogen atom. All right, so that's our standard. So we're going to look at this equation here. This right here, this one in the middle, I want you to kind of just look at it, but don't feel like you need to use that. Okay, it's probably easier to use this condensed form down here. All right, specifically, you get the little dry guy again. This part. So the energy of the photon is equal to this constant that you're going to know, 2.18 times 10 to the negative 18 joules, times, and notice that bracket there, 1 divided by n final, which is your final energy level, minus 1 over n initial, which is your initial energy level, and those energy levels need to be squared. Okay. Also notice that the energy of a photon can also equal hc over wavelength. Okay. It's important because hc over wavelength then can also equal this whole equation here. Sometimes people like to make that direct connection. Sometimes people like to do things in 2 steps. That's fine. But we are going to look how we can calculate different parts of this whole process here. Let's go back there. The other thing I want you to notice is this difference here. We have the energy of a photon, that's the thing that is released, versus the energy of the atom, okay? Notice that there's a negative sign in front of the atom, and there is not a negative sign in front of the photon. That's because these two values have to be opposites of one another, right? It's like back in chapter 6 in the thermochemistry section when we said the heat that is released from one thing has to be absorbed by the other thing. So in this case, if an atom releases energy, that energy is transferred to the photon. If the atom absorbs energy, it's absorbed from the photon. So whatever the amount is, though, these two things will be opposite values of one another. Okay? So when a situation is being described to you as a certain wavelength of light is hitting a metal, what's the energy? Well, they're describing the light that's hitting the metal. The light that's hitting the metal is a description of the photon. All right? It's figuring out the energy of the photon is just a different question than what was the energy of the atom involved. But when you find one, you can find the other then, all right? Because they're directly related values. And this, again, this is a much better description of what the difference in energy levels of these transitions look like. And notice how big the gap is from n equals 1 to n equals 2. And notice how the size of these gaps decrease as you get further and further away from n equals 1. So if we wanted to know which transition emits light with the shortest wavelength, what does the shortest wavelength mean? Shortest wavelength means the highest energy, okay? The highest energy means a transition that happens closer to the n equals 1 level. All right, so the biggest transition between all of these options is the transition from n equals 3 to n equals 2. If we look back here at 5 to 4, 4 to 3, and 3 to 2, clearly 3 to 2 is the biggest transition. So that's the most energy. So the shortest wavelength is equivalent to the most energy. Let's determine the wavelength of light emitted when an electron in a hydrogen atom makes a transition from in n equals 6 to n equals 5. So it's going from 6 to 5. That means that it's relaxing. That means that it's going to be releasing energy. Okay? And we want to know what the wavelength of the light is that corresponds to this. So the first thing that we might want to do, okay, we want to, okay, again, I put both forms in here, but I would focus in, let me square it off here. I would focus right in on this. Okay, that is the version of the Rydberg equation that you can use. Also, coincidentally, if you got rid of this negative sign now, because right now, if you look here, this is the E for the atom, right? If we're trying to figure out the wavelength of light that an electron is emitting, that has to do with the energy of the photon that's traveling out. So in this example, we're solving for the energy change of an atom. Okay, the energy change of an atom is going to be opposite in sign to the energy change of a photon. Right? So right now we have the negative sign in front of our Rydberg constant because we're solving for the energy of an atom. But I'm just trying to say that, just make sure that you know that that's going to be opposite for energy of a photon. So I don't know if it might be easier for you to just start by solving with energy of the photon instead. You can do that. That would be fine. But notice the constant here is 2.18 times 10 to the 18 joules. And then in parentheses, I have 1 over my final my final level squared minus 1 over my initial level squared. Do everything in the parentheses first. So 1 over 25 minus 1 over 36. Get that number, then multiply it by the Rydberg constant. And that is your value in joules. So that's the energy that the atom was releasing. Okay? So that means that this is the energy that's going to be associated with the photon itself. Now we're not done here because the question wants to know what the wavelength of light emitted was. Well, now that we have the energy, now we can find the wavelength. Probably should get rid of those pictures. Okay, so now we're back to our E equals hc over lambda. But now we're going to solve this for lambda. So we know Planck's constant, we know the speed of light, and now we know this energy value because we just found it using that Rydberg equation. Okay, so now we'll solve that and we get a speed of light that is in meters. Please be aware that a lot of times you are going to be asked to convert your wavelength. Did I say the speed of light in meters? I meant the wavelength in meters. This wavelength value is in meters. Oftentimes you're going to be asked to report it in nanometers. So just please be used to doing that conversion. Okay. Why don't you try this one? Determine the wavelength of the light absorbed when an electron in a hydrogen atom makes a transition from an orbital in which n equals 2 to an orbital in which n equals 7. I'm going to do this one on the whiteboard for you guys. Okay, so here's the question that we're looking at here. So we're looking at this transition from n equals 2 to n equals 7, all right? So I'm going to set up my equation, 2.18 times 10 to the negative 18 joules. My n final is 7, so it's going to be 1 over 7 squared minus 1 over 2 squared. Okay. And now I want to actually get a value for this. So 1 divided by 49 minus 1 divided by 4. Okay, and I'm going to get 2.18 times 10 to the negative 18 joules times 0.22 times negative 0.22959. Okay, multiply that by my Rydberg constant. Okay, so this right here is the energy that's going to be associated with the photon. Okay, now let me just fix that real quick. Here's what you have to start to associate in your head. If you have this negative sign here, what that means is that the photon is the thing that's going to be supplying the energy. All right, so in this case, we're going from n equals 2 to n equals 7. That means that our atom required energy. That means that this negative sign here means that the photon gave this amount of energy to our atom for our atom to make that jump from 2 to 7. Okay? Now we're going to use this information and we're going to figure out what that wavelength was. But a wavelength is not going to be a negative value, just like a distance is not a negative value. So we're not going to use a negative sign to calculate a wavelength value. So, okay, we know that's our formula. And then we're going to solve it for wavelength. So we can switch places there. Wavelength equals hc over E, 6.626 times 10 to the negative 34 joules times seconds times 3.00 times 10 to the 8 meters per second divided by 5.005 times 10 to the negative 19 joules. And let's see what we get. Okay, I got 3.97 times 10 to the negative 7 meters. And now if I wanted to convert that into nanometers, which again, you should be used to doing, 1 meter is 10 to the 9 nanometers. And this is a good example of why we do this. It's because it's just 397 then. And that's a nice and friendly number. Okay. Oops. All right, so why don't you try this one? Find the principal energy level to which the electron relaxed. Okay, here's our next problem. So now to answer this question, right, we are looking for this value here. We're looking for what energy level this electron relaxed to. We're given the initial energy level and we're given the wavelength. So now we have to work a little bit backwards here. We're going to use this wavelength and we are going to find the energy that's associated with it. Once we have the energy, then we'll be able to solve for this final energy level value. All right. But we need to do an energy calculation first. This has to be in terms of meters for us to use it down here. So let's do a little conversion. There's 10 to the 9 nanometers in 1 meter. Okay, so I've got my Planck's constant, I've got my speed of light, I've got my wavelength in meters, and now I'm going to calculate the energy that's associated with this. And I get 2.119 times 10 to the negative 18 joules. Okay, you see where that all happens, right? So that's my energy value. Now that I have my energy value, now I can go ahead and solve for my Rydberg equation here, right? So I'm going to have 2.18 times 10 to the negative 18 joules. Now, in this case, we need to like think back here, okay? Let me switch back before I go any further so we can reason some of this out. Let's share the screen again. Okay, so an electron in the n equals 6 level of the hydrogen atom relaxes to a lower energy level. That means that the electron is going to be releasing energy, okay? You got to keep that in mind when we're looking at the signs here, all right? Just to keep it in mind. Let's keep on going. 1 over, we'll call it x squared minus 1 over 6 squared. Okay? So now we have this value that we're going to plug in here. 2.119 times 10 to the negative 18 joules equals 2.18 times 10 to the negative 18 joules, 1 over x squared minus 1 over 36. Now what I would recommend doing once I got to this point is I would divide both sides by this Rydberg constant to get rid of it. Okay, let's get a number for that, 2.18. .972 equals 1 over x squared minus 1 over 36. And I do that because now I don't have to worry about this whole fraction situation. I'm just going to add 1 over 36 to both sides. And we're going to I'm going to erase the top of this. So we can keep on working. Just switch colors so we can keep it separate. So 0.972 plus 1 over 36 is 0.9999. Okay. Now I'm going to multiply both sides by x squared. So 0.9999 x squared equals 1. X squared equals 1 over 0.9999. So x squared equals just about 1. So if we take the square root of that, it's going to equal 1. So our n final is level 1. Okay. So hopefully you are finding that to be an okay process. I think it's pretty straightforward. But that's really that's all the math for this chapter. And those are all the concepts. So give it a whirl, give your master in chemistry a whirl. If any of this stuff seems confusing, please let me know as soon as possible so we can clarify it.